If you have to catch a bus which arrives at 9 o'clock in the morning at the bus stop, and if it takes 15 minutes from your house to reach that bus stop, what time will you leave from your house? Isn't it 8:45? What happens if you leave at 9 o'clock from your house? You will not catch the bus, right? So this is the same scenario which happens in digital circuits when we deal with the flip-flop and its setup time as well. So setup and hold time violations are very crucial in timing of digital circuits, and these setup and hold checks ensure the timing of the digital circuits. Let's see why the setup and hold violations or setup and hold checks are required. These synchronous checks needed to ensure that the proper data is ready and available to capture and held for at least minimum time so that there is no unexpected pass-through of data through the flip-flop. So there are two types of checks here. One is the setup check, which ensures that the data is ready and available at the required position to capture that data. And the second check is the hold check, which ensures that the data is held for some duration so that there is no unexpected next data comes and disturbs this existing data, right? So these are the two checks that we are going to do. Let's understand with the flip-flop in VLSI how actually this works, right? So this is the diagram of the flip-flop which is used in VLSI. There are different types of flip-flops with different gates that are possible, but this is the type of flip-flop which is used in VLSI, as we know, since this is a bistable multivibrator, right? This is the simplest static bistable multivibrator that exists. So if you see this, let me take a laser pointer. So this is the pass transistor, and now this is inside the flip-flop, right? What is actually the setup time? Let's understand that. I have this is a master-slave topology. So the clock is the controller which controls the data transfer here. So when clock is 0, the data is transferred here to these NOT gates, and since when clock is 0, this is 1, right? When clock is 0, the data is latched in, and when clock is 1, it is transferred to the output. That's how it works, right? So if we want to define what is setup time, so the data takes some time to reach this point, right, through these NOT gates, to these NOT gates. So the propagation time from this D input pin till this pin of clock, right, this pass transistor where the clock arrives, this propagation time is actually called setup time. This is the reason why we have setup time. So inside the flip-flop, this is the propagation time which leads to the setup time, and inside the flip-flop, this is the time which is the reason for hold time. So what happens, let's understand this. See, if the data is coming, okay, the data has arrived at a D pin and it hasn't reached this point, which is the output of this inverter, the second inverter, and your clock arrives, okay, but the data is not ready at this pin to transfer it to the output. Since it's not ready, so that it cannot transfer anything. So that is why we are saying this is the setup time. Some kind of setup has to be done before this clock arrives, right? So that is it's kind of a preparation for the data transfer, which is controlled by this clock. So similarly, when let's say the data has been transferred to the output of this pass transistor, but it is not held before it is transferred here. The data takes some time to reach this position of the inverter output, right? So imagine that the data is propagating, okay, it's going like this, it's going like this, it's going it went to the output of this inverter, and immediately the data has been changed at this input, okay, and that makes some kind of a disturbance to this input, because there is a propagating data already, and this data also comes in. If this data is which is going is 0, and there is a data which comes 1, and then there is a ambiguity at this line whether which data has to be transferred, right? That is a discrepancy, and that should not happen. It disturbs the input change, disturbs the propagating data. So if it should not happen, there should not be any change in the input before it is getting transferred to the output. So that kind of timing is actually, that requirement is called hold time. But I want you to think one thing, that setup and hold time and setup and hold checks are two different things. They are not the same. Setup and hold times are the requirements of the design, right? They are fixed. If we have a standard cell of a flip-flop, for that standard cell, the setup time is fixed. And that is the requirement. And setup and hold checks are to ensure, those are the checks to ensure that these setup and hold times are really met. Okay, so there are two different things, right? This is a requirement, which is the setup and hold time. The setup and hold checks are the checks to ensure that these are done. So let's define what is setup and hold time first, formally. The setup time of a flip-flop, it's related to flip-flop. It's not related to the digital timing of digital circuit, entire digital circuit, which may happen in different scenarios, right? I'll show one scenario later, but so setup time, when we say it's related to the flip-flop itself, and setup time is only defined for the synchronous flip-flop, right? It is for the latch, it is different. For latch, we say removal and recovery time. Those are different things. This is only for the flip-flop which is an edge triggered flip-flop. Okay, so setup time of a flip-flop is minimum time for which the data needs to be stable before the arrival of active edge of the flip-flop. So that's the minimum time that is needed. So what we are saying is it's the time required for the data from this D pin to reach this pin. So this much time it has to be stable. The input has to be stable before the arrival of the clock. So that is actually the setup time. Okay. And the hold time is the minimum time for which the data has to be stable after the arrival of the clock. That is actually this propagation time itself. So we will see in the timing diagram that if we consider, if there is a data which is being launched from the previous flip-flop, it can have one cycle to reach the next flip-flop. Okay, but it doesn't have full cycle, because there is a setup time also for this flip-flop, right? So that setup time is this much, right? If this is the setup time before the arrival of the clock, this is the next clock edge which is coming. Before the arrival of this clock, the data has to be stable at this flip-flop, at this point. Data has to be stable at this point. So this much propagation delay has to be subtracted from one clock cycle to make sure that the setup time is met, right? Similarly, the hold time is this. After the arrival of the clock, the data has to be stable for some time. That is the time which is called a hold time. So if you consider the D input, if D input comes a little late, this is the situation where it is meeting both setup and hold times, because the data is arriving before the setup time and data is still stable after the setup time, hold time, right? If it comes a little late after this dotted lines, imagine this 0 to 1 transition is little late, it's here over here, then setup time wouldn't be met, because it will not be able to reach this point where it has to come after this like output of this inverter, and it can be propagated to the output, right? It cannot happen, right? So similarly, if it changes before this hold time, it is not changing, it is at the one level. But if imagine that it is changing before this hold time, then also there is an ambiguity, and hold time is not met. One more question is, can the setup and hold time be negative, right? This is one of the question that is being asked. So setup, yes, the setup time can be negative, and yes, the hold time can also be negative. We can make them negative by maybe adding. See, how can the setup time be negative? We can ask the question. Like if the propagation delay of this path is less than the clock path, right? Clock takes some time to reach here, this point also. In that path, if we add some delay, then this can arrive a little late, right? So we can make a setup time negative, and we can make a hold time negative also by making the reverse, right? We can make this, we can add some delay in the setup time, right? If we add delay in the setup time itself, then it takes like for the whole time, it has more time. It has more time to reach this path, right? If the propagation delay of this path is less than the propagation delay of this path, then we can say hold time is also can be negative. So both can be made negative by making some arrangements in these paths of output path, or in this setup timing path, or clock path and delay path, sorry, data path. So this can be done. But can both be negative at the same time? Can both setup time and hold time be negative at the same time? No. The reason why it is no is because both, like if the whole time is some negative value, the setup time has to be positive enough to make the sum of these positive. If you want to see why it is so, if you see this diagram, right? So timing diagram, whole time is made negative. Okay, we agree with that. And if whole time is negative, by definition, it is after the arrival of the clock edge. But since it is negative, it is coming before the arrival of the clock edge. Now you see the whole time is here. But by definition, it says the data has to be ready. And after that, we call it is a whole time, right? So if this is this whole time, then the data has to be already captured. And that means the setup time is already done, right? So setup time has to be positive enough. This is the setup time, right? So this setup time increases as hold time decreases. So this is a requirement, and this setup plus hold time, this can never ever be negative. Okay, so this is a positive requirement. So if we make some arrangements to make the whole time negative, we may end up being setup time positive. So that becomes a problem. Again, the vice versa is also true. So if I have to give an example of the situation of setup and hold check, so till now what we have discussed is setup and hold time and its definitions, and those are the requirements that we have. Now the situation where what I'm discussing is the setup and hold check. How do we ensure these setup and hold checks are met in the design, in the digital circuit timing, right? So if you consider a reg to reg path, we call this as reg to reg path. Different types of paths, timing paths are available there in the STA, which is static timing analysis. I'm not going too deep into those things, but if you consider this reg to reg path, there is a flip-flop here which is called a launch flip-flop, and there is a flip-flop here which is called a capture flip-flop, because the data is launched from this launch flip-flop and captured at this capture flip-flop. Now the clock is being supplied to both of these flip-flops, and there is a combinational logic in between, which I have made it as a small block, but there could be multiple combinational logic. Okay, so now what do I need to ensure? The first thing is that the data can take one clock cycle to propagate from this flip-flop to this next flip-flop, which means it cannot be late than one clock cycle. That is true. And we also came to know that data cannot take one complete cycle, because there is some setup time for this flip-flop, which means there is some propagation delay inside this flip-flop, which we have seen already, right? So from this D pin to that output of the inverter, second inverter, where there is a pass transistor. So it has to reach from here to that output of the inverter. From here to here, that is setup time. So the total time from this Q output to this output of the inverter is 1 clock cycle. So what is the time available to reach this D input? That is actually the 1 clock cycle minus this setup time, right? So that is the actual equation that we have. If you see this, the setup check ensures that T flip-flop, which is this T flip-flop, okay, this is assuming that the clock is arriving. Clock arrives to this flip-flop, this clock pin, and this capture flip-flop clock pin at the same time. Imagine the clock is arriving here also and here also at the same time. There is no latency, there is no discrepancy of the clock arrival. The clock arrives simultaneously. If that is so, then the T flip-flop, the propagation delay from this clock pin to this output, which we have seen, which is the whole time actually, but this is the propagation delay. So T flip-flop plus the T combinational logic must be less than T cycle minus T setup. If this is satisfied, then we can say the setup time is satisfied, that the data arrives here and it will be completely set up, right? And it is ready for the launch, or it is ready to pass by that pass transistor, which we have seen. But what happens if there is a discrepancy? There is the launch time, the launch clock path is the propagation delay of the launch clock path is different than the propagation delay of the capture flip-flop. So in that case, we have to consider this also, which is a T launch path and T capture path. So this entire path has to be considered. T launch plus T flip-flop plus T combinational must be less than the total cycle minus T setup plus T capture path. So if these equations can be like, maybe sometimes it is different. Some people write it in a different manner. So if like they consider skew, they consider clock skew, and they write it in this side as a T skew, okay, clock skew. So this is also true, because see, if clock comes late here, which we call as a positive skew. If clock comes early to this launch flip-flop and clock comes late to this capture flip-flop, then it is a help for actual setup check. So for setup, it is a very good help, because this increases the time for the data to come and arrive at this point, because clock itself is coming late. So the data also can come a little late. So that is good for setup, but it is bad for hold. We can say, so again, these kind of things are always a trade-off between setup and hold. For the hold check, which it's a similar thing. As we have seen, what the hold time says is the propagation delay of this path cannot be lesser than this hold time. Okay, so it says it should be at least greater than the hold time. If it is lesser than, if the propagation delay of this path, if this data path takes lesser time, then it can disturb the existing data which is over here already. So capture flip, this has to satisfy for the whole time to work, right? So similarly, if we consider the skew, this is the equation that we can consider. But remember that what this setup and hold checks in this circuit, digital circuit, ensure is that the data can take some minimum time, and data cannot take propagation time which is below some value. Also, it cannot take propagation delay, value of propagation delay above some value. Also, there is a restriction for the propagation delay itself, right? The propagation delay of this path, data path, is restricted some between minimum and maximum values. Those minimum and maximum values are T hold and T setup, actually T cycle and minus T setup. right? This is the minimum value that it can take. It has to be greater than t hold, the propagation delay, and it has to be lesser than this value, which is t cycle minus t setup. So this is the minimum and maximum value of the propagation delay of the path itself. So finally, you can discuss metastable states. What happens if there is a violation of setup and hold time? Till now, I have said that it cannot violate the setup check and it cannot violate the hold check. But what happens if it violates? I have said some ambiguity will be there, and if it doesn't arrive at if the setup time is not met, which means if it doesn't arrive at the particular time, nothing will be transferred or something. But it really creates a problem, what is called as a quasi stable state or quasi static state, which is called as metastable state, which is a kind of a state between 0 and 1, and it will be bouncing back 0 1 0 1 0 1, and finally gets after maybe a few fraction of seconds, it will go to a stable state, whether it's 0 or whether it's 0 or 1, but it will go to a stable state. But it is completely undeterministic. We have no control over whether it goes to 0, whether it goes to 1. We have no control, which means the chip itself becomes undeterministic. The output itself becomes undeterministic, and it's very bad, and it destroys the chip itself. The functionality is completely destroyed. So in order to avoid this, we must ensure that the setup and hold checks are always proper, and we ensure that the timing is clean, and setup and hold checks are always met, right? Setup and hold timings are always met in the design, so we will never end up in the metastable state. That's all for now. Thank you for watching. Bye bye.